and better still, how science can help them get on with their hobbies. I think that's really, really interesting and exciting. And I've got 5 little kids, so I have no hobbies. My kids have hobbies.
I have hobbies.
So, you know, the oldest is 17 and the youngest is 3. So I have my hands full all the time. So it's a real pleasure to talk to you all. I know you're coming at this from all over the place. So I'm going to put this in play mode, and I'm going to attempt, see if I can move. Hold on, I got to put it out of, there you go. All right. Just navigating the Zoom nightmare. So I don't know if I'm going to be easy enough to spot if questions come up. So what I may do is just pause a few places throughout the presentation for some questions, and then we can do deeper Q&A later. So here we go. Okay. So like, I always give this crap introduction, this talk about these 3 old dead guys. And the story is really about these 3 dead white guys and their contribution to solar physics and statistics and mathematics, and how each one of them has kind of influenced our work that we've been doing over the last decade. We made a discovery about probably the middle of 2011, and it took us 3.5 years to publish it. Such was the fervent joy amongst my peers as to what it meant. We've been tracking that prediction since then, and it hasn't budged one single bit. So I'll walk through that a little bit. I'll probably jump over bits, but if I'm not given enough detail, just holler. So the old dead white guy on the left is a guy called David Hilbert. He's a very famous mathematician. The guy on the right is George Ellery Hale. He's a very famous astrophysicist. In fact, he invented the field of solar physics. And the dude in the middle, I don't know, he's just a bit part in this show. And his name is Charles Tree, Chree. He's a fellow Scot. And he was the director of Kew Observatory round about the time of, I think he was maybe a PhD student around the time of Carrington. So if you know the Carrington flare, and so he was in charge of all the magnetometers and things like that in the UK, and he has a very interesting track record. But he's very, very famous for one thing. And that one thing has been stolen by the meteorologists. So we'll get there in a little bit. So maybe we'll try and recover that kind of statistical brilliance for the solar physics community, since that's where it originally came from. Just want to give credit to my co-workers and colleagues. They're listed at the bottom. And a lot of this work is actually a credit to folks that, unbeknownst to me, published similar work in the 80s. Back in the day when they had a lot of data, they're very careful with their data. There was a paper, when we were writing up our discovery in 2011, I was 95% of the way through the paper when I realized that someone had published something quite similar in 1988. If they published it in Nature, and it was like a dirty secret. So all of my colleagues knew about it, but the paper only had a tiny number of citations. So usually that's an indicator that everybody knows about it because it impacts their work, but nobody cites it because of the danger of citing it, because of the implications that it has for what they do. But I was trained to challenge everything. So what you're going to see is a very non-conventional approach to understanding the sun. So I'm going to go into this beautiful movie that was built by my colleagues in Norway, and it was a full disk image. And the idea here is just to set the scene that these are not sunspots. These are just small pores. The scale on the side of the image is changing rapidly. I'm going to play it again. So from full disk, we come in and zoom in on that small set of pores. And of course, you'll all probably know that sunspots are a magnetic object. And in fact, our star, the sun, is a very, very magnetic object of its own. And in fact, it's that magnetism that gives rise to a lot of the disturbances that my old lab is particularly worried about, because that magnetic field gets tossed around in the large spaghetti pot of the interior of the sun. It gets twisted, it erupts, and some of those eruptions hit the Earth. And that was my old job, was to understand and predict when those were going to happen and what impact they would have on us. Now, Paul was on another talk last night, and I'm sure they showed a movie like this or one very similar to it. And what it is a tracing out of the sun's magnetic field over time. So after it's traced out the central meridian of the sun, it's a play through. And so you're watching just the evolution of the sun's magnetic field and this bizarre phenomenon called the Hale cycle. So the sun is kind of well known for having a 11-year sunspot cycle, but not so many people know that their sun also has a 22-year magnetic polarity cycle. So if you think about that in the context of the Earth's magnetic field reverses, but it does so on a time scale of about 100,000 years. So, however, the object at the center of the solar system has a magnetic field that flips every 22 years. So, and believe it or not, is as regular as clockwork. So one thing to take out of this movie is that these magnetic fields, they may look random, but they're not. Where these magnetic field things, the blue and yellow things, pop up is not random. There's an element of randomness to it, but it's what I'm going to show you is that it's highly organized at a global scale. The other thing to bear in mind here is that these objects, which are of the scale of about 5,000, about 1,000 to 5,000 Gauss in strength, are the literal tip of the iceberg. And so if I get to that point, hopefully I'll get to that point much later, you'll maybe understand a little bit more what I'm talking about. But this is a pretty beautiful movie. It's built over 30 years. So, as I said earlier, the sun spots wax and wane in number over the timescale of about 11 years. And that, from this plot that's on the top here, you'll see that, the periodicity of this solar cycle, the sunspot cycle, varies everywhere from 8 years to 13 years. Actually, there's a 14-year long cycle. And on top of that, the envelope, the modulation of the sunspot cycle goes up and down. So it produces events like happened around the turn of the 19th century, which we call the Dalton minimum. And then there was another mini kind of minimum in the late 1880s, early 1900s, before it peaked in 1956, I guess, was the top of cycle 19. The cycle 19 played havoc with the early Apollo missions and with the Mercury, Redstone, Gemini program, and all kinds of other fun stuff. But anyway, so this is a truly age-old puzzle. The puzzle being, how does this sunspot cycle work? And I'll tell you, there's at least, there is at least 250 years of observations. There's probably at least 250 published solutions to that puzzle, maybe 250,000. And, if you are or are not aware, there's probably at least 250 predictions of what the next sunspot cycle is going to look like. And I'll tell you that they're probably all wrong. Because nobody truly knows what this monster is going to do. And anyone that's tried to predict its behavior in the past was, wrong. So I'm going to dial in a little bit further and only show you the last 22 years. Actually, it's the last 24 years of data. I'll point out a few things. So the top plot is the daily sunspot number. And there's a few things you can point out here. Black trace is the total number. And I've separated the two hemispheres in red and blue, north and south. One of the things you'll notice is that that is not very smooth. There are massive excursions on this plot that aren't the subject of this talk. And you'll notice that over the time scale of about a year, there's a massive oscillation on top of what would be considered to be a pretty smooth variation. You'll see that some of those peaks and troughs are in the northern hemisphere and some are in the southern hemisphere. And if I look down to the distribution of spots that I show below, you'll see clusters where it's very intense. If I look at the start of 2012, for example, a very intense cluster of sunspots in 2012. And a very strong asymmetry between the two peaks of cycle 24. Not only that, of course, is the drop in cycle 24, but the issue here, the thing to grasp here are these massive surges in sunspot production. Those also are not random. And believe it or not, they're to do with similar effects going on inside the sun, like the Gulf Stream and the jet stream on Earth. So on my first slide, talk about buoyancy. Buoyancy is a very important phenomenon when it comes to sunspots. And so just like features in the Earth's atmosphere, buoyancy of air parcels becomes important for weather, and it's also critical for what goes on inside the sun, especially its magnetic fields, which tend to be, they have their own pressure. One of the things that we're worried about right now is when does sun's solar minimum end? And I'll tell you that a lot of my colleagues don't really know what solar minimum is. They define it as being minimum of the production of sunspots, and that's fine, but it doesn't mean a lot physically. Because if I put a map in my sunspots of what the Hale cycle looks like. So this is the 22-year magnetic variability of the star. So the red and blue here is a theme that you'll see throughout the talk. And it shows the progression of different magnetic polarities, blue being negative, red being positive, and how they interact with one another. And so you'll instantly notice something very peculiar about solar minimum. So if sunspot minimum is here between 2007 and 2010, there are 4 oppositely signed magnetic bands within 35 degrees of the sun equator. Our hypothesis that we came up with in 2011, was that those 4 bands basically cancel one another. Right? The magnetic fields always want to cancel each other out. It's one of Maxwell's laws that magnetic fields always want to cancel. And so these magnetics basically cancel each other out until it comes to a point in time where the magnetic field basically dies. If I look back in late 1997, the magnetic field at the equator basically dies, and instantly we see sunspots popping up at mid-latitudes, right? But the difference is that the band on which those sunspots form had actually been around for about a decade before that, okay? So what you're looking at is a large-scale interacting magnetic system, and it always wants to cancel itself out, right? So it's almost always in balance. And remember that later, because remember I said that we're only looking at the tip of the iceberg, right? So what you're basically looking at with sunspots is the imbalance in the system, not the actual magnetic field at the bottom. You're only looking at the difference, okay? Just bear that in mind. So sunspot minimum ends when a Hale cycle ends. So this 22-year cycle comes to the equator, it dies. When it dies, it gives rise to the new sunspot cycle. Here's more data to illustrate what that means. So I'm going to show you the overlap. So what's on the bottom of this plot is a schematic, right? It was drawn based on measurements that we took. The top plot and the plot on the right is part of the data that we used to construct that. And these are tiny little active regions on the sun. The sun is completely pockmarked with them like a teenager. And what we're looking at, if you look at the 2007 to 2012 timeframe on this plot, you'll notice that these magnetic bands clearly overlap. Now, if I go back here and you look at just the trails of sunspots, there doesn't seem to be any appreciable overlap at all. But at smaller scale magnetic features, that overlap can be almost as much as 6 years. In fact, it's much more than that. But on this measurable, it's 6 years. Now, I'm going to clue in. If you look around 2011, you look at the equator, do you see something rather abrupt that happened? The equator has a bunch of these features that we call EUV bright points, and all of a sudden, none. And right after that, none, is exactly when the big sunspots appeared, late 2011, or sorry, in middle of 2011. That event, is basically signaling to us that the magnetic field of the Hale cycle just died. So when the Hale cycle ends, this is the kind of behavior that the sun exhibits. I'll show you another nice example of that, but I'm going to show you an animation of how these triggers work with respect to sunspot production. So again, our schematic shown, and over the top of it, I've plotted two different kinds of data. You don't need to worry about the green one, but just look at the spots. So you can see that the interplay between these overlapping magnetic systems, that the sunspots are basically riding on them, okay? So you can think of, you guys are radio wonks, so you can think this is just one big interference pattern, right? Why is the event that happened in 2011 so significant? Well, what basically happened with the sun is its magnetic environment changed in a heartbeat. And right here, I'm showing one particular measure of the sun's corona. So you guys may be familiar with the F10, 10.7 centimeter radial flux that they measure up in Canada and a few places around the globe. It basically measures the activity level of the sun's corona. And that then gives rise to models of ionization in the ionosphere, et cetera, et cetera. And so you guys, when F10.7 kicks up above 90, you get nice transmission around the world. But what happened with the sun on February the 11th, 2011, or there or thereabouts, with the corona, the radiation from the corona increased by 85% almost overnight. That sounds ridiculous, but it's true. Over a span of 2 weeks, an object the size of the sun basically went into overdrive. Okay, the magnetic field just changed. And so when we tried to publish this, now we published this late last year, or middle of 2018, but it was another one of these uphill struggles. Nobody could believe that the global scale magnetic field of a star could evolve this quickly. The other interesting part of this work is that when you look, the sun's a bit like an onion. And when you look at different layers of the onion, they respond in different ways to what you're doing with the magnetic field. Below about 1 million degrees, so the sun's outer atmosphere peaks at around 5 million degrees. Below about 1 million degrees, there's only about a 5% change in the atmosphere before or after this magical event, right? Above 1 million degrees, it peaks out at that 85% mark, but the corona really goes through a step. It takes 10 years to recover from that step. Okay, so it basically lights up and it's on. If we go back in time, so I'm now looking at 2 sunspot cycles now. If I look at the flux of the 10.7 centimeter radial flux, and we focus in again, look at February 11th, 2011, F10.7 just jumped through the roof. And it pretty much never came back again. Okay, so you can see these basically step functions in the data are the signature of these Hale cycle endpoints. When the Hale cycle ends, the magnetic field erupts. Okay, now I'm showing you 6 of them. Okay, so I've gone from 1 to 2 because it wasn't good enough for my peers. 2 wasn't good enough. 5 was marginal, just lucky. If you start to look at F10.7, the record of daily S is the weekly average F10.7, you see these step functions in the data. Those step functions coincide with the end of Hale cycles and the start of what is known as the butterfly wings. This is the infamous butterfly plot, right, of Maunder, where if you look at it side on, these look like butterfly wings. The butterfly's wings start at about 30 degrees latitude, but they coincide with this event at the equator that we have called the Terminator. It basically, because it's the termination of Hale cycles, but it also gives you an opportunity to put big pictures of Arnold Schwarzenegger on the screen. So there's 5 of them. There's 13 of them. And so if you go back 140 years, you can notice something else when you look at different solar phenomenology. Now, if any of you have looked at a lot of images of the sun, there's this feature that appears around the edge of the sun called a prominence. And, you know, like all good astronomers, they use very obvious language to describe stuff. And the reason they call them prominences is because they look very prominent against the disk of the sun when you look at them in a certain wavelength. Can someone mute, please? Okay. So I'm going to show you the filament record over the same time frame. Okay. This is the filament density record over 140 years. So this goes all the way back to the dawn of photography. You'll notice a few things. 1, you'll see our terminator points in. But 2, if I encourage you to look at high latitudes, you see these beautiful wispy excursions. Okay. In the late 60s, they discovered these things, and they associated with them with the start of the sun's magnetic reversal process. So basically, they assumed that the sun's magnetic field evolved from about 55 degrees latitude, moved towards the equator, and then the polarity flipped. So that every 22 years, basically this process happened. There's a small caveat to that. If I look now at the data again, and I only plot the highest latitude prominence in the system, you'll see how beautifully regular it is. And also you'll notice that the magnetic field basically sits at about 55 degrees latitude and makes that excursion one time. So it sits at 55 degrees latitude, something happens at the equator, and boom, off it goes towards the pole. It resets itself, boom, there it goes. It's the clockwork. So this, whatever's going on in the sun's interior has global effect, right? So when the Hale cycle ends at the equator, not only is its influence felt at mid-solar latitudes, its influence is also met at high solar latitudes. So you're looking at basically a tsunami, right? So you have one event that goes off, and then it transports itself, and the sun changes over the timescale of 1 month. So 1 solar rotation for us. That is mind-boggling to most astrophysicists. Okay, so I would tell you that 13 of these is just lucky, right? That's what my people tell me. It's just lucky. Okay, 13 of them or 14 of them, just 14 coincidences. Okay, so there's 3 things to establish. this came out of the part of the peer review for this work, okay? You've done this in a very subjective way. Is there a way you can develop an algorithm? Because usually you try to do the impossible to stop things from getting published. So can you do it algorithmically? Then can you predict when the next termination point will occur? Because in our paper, and it finally got published in 2014, we said it would be probably towards the end or the middle of 2020, right? Based on measurements that we took in 2011, okay? And then one of the things we noticed, and if you pay close attention to the separation between these events, was how does the separation relate to the cycle strength? Because that is the holy grail of maybe not the holy grail of astrophysics. It's an important puzzle for astrophysicists, is to be able to predict what the next solar cycle looks like. And if you look at this quite carefully, you'll notice that when these blue vertical lines are more separated, the amplitude of the sunspot number goes down. And when they're closely packed, the amplitude goes up. Now, if I was to jump back in my slide deck and go back to my schematic, let me go back to here. Okay, actually, I'm going to go to the next one. What we're basically saying is that the degree in overlap between these magnetic systems determines how strong the cycle is going to be. And if the end of my Hale cycle moves too far to the right, it actually starts to interfere with the growth of the next one. Okay, so basically what happens is the cancellation period that is solar minimum basically extends. We can talk a little bit later about how that actually happens, because it could be very odd, but the cancellation basically impacts the ability of the sun to grow spots, okay, because it's all about buoyancy. And buoyancy in the inside of the sun is all about the amount of free magnetic field that you have. So I'm just trying to find my spot here. So let's see if I got through here. All right. So I'm going to set about doing my algorithm. And this is where David Hilbert comes in. And you guys, in dealing with all your signal analysis, probably know about David Hilbert. He wasn't quite as orthogonal, pardon the pun, as Fourier. And he thought that Fourier analysis was limited because it only applied to fixed phase signals. But Hilbert was fascinated with time series analysis, and so he developed a different trick for time series where the phase of the signal so this time series isn't stationary. So the phase is also varying with time. And guess what? The sunspot cycle is one of those types of signals. Even though a lot of my peers will throw Fourier transforms at them to the end of time, okay? Fourier transform probably doesn't even apply. So the top of the plot is my F10.7 signal. This third panel here is the hemispheric sunspot number. And the two things that plot are the outputs of a Hilbert transform to those time series. One is the phase function, the amplitude function. So basically the Hilbert transform is looking for the maximum rate of change of a time series. And so when you've got step functions in your data, you would expect that the amplitude function peaks there. And lo and behold, if I look in F10.7, you'll see that the amplitude function of the Hilbert transform peaks at the termination points. But there's another very interesting phenomena that if you look at the phase function, so how does the phase of the Hilbert transform vary as a function of time? And you'll see that coincidentally, at the termination point, the phase goes through a 360-degree flip. Okay? So the phase slowly varies linearly, and then at the termination point, it flips. Okay? So this is a very characteristic signal. In fact, maybe at the end, we'll come back to this interesting feature in 2003. We have our own suspicions about that, but it's kind of cool how, see how the gradient changes? Something very weird happened in late 2003. but we'll get to that in a bit. So in principle, if I had to take my random time series and just run it through this calculation and figure out when the phase flips, I now have an algorithmic approach to mapping out where all the termination points are. So where are the end of my Hale cycles, right? And I'm going to jump now to use the entire sunspot time series. So you don't need to worry about all the plots here, but the black dots here are the daily value, monthly values, sorry, weekly values. The red curve is a smooth version of it. The blue line is a trend of the data. The second panel is when I remove the trend from raw data. The third panel is the amplitude function. So remember, it peaks at the maximum rate of change of the time series. So not at the maximum of sunspot production, but at this time at the bottom where the terminator occurs. And then here's the phase function. And instead, I shifted the phase by 180 degrees. So now instead of looking for where it switches, I'm looking for where it goes through zero. You can do that almost arbitrarily. And these yellow diamonds are the terminator definitions just based on our analysis in 2014. Okay, so basically the algorithmic approach validates what we did. Okay. Now I'm going to do an experiment because you're all really interested in cycle 25. And my hunch was that the separation of these events gives you information. Okay. Now, I'll say it again. Sunspot cycle, the sunspot minimum is the result of interference between 4 magnetic activity bands. Count them. Negative, positive, negative, positive. They're canceling each other out. When the positive and negative ones at the equator die, you get rampant sunspot growth on the 2 remaining bands at mid-latitude. As those evolve in time, they start to feel the influence of the next Hale cycle, then actually turns them down, right? Because you're starting to increase the amount of interference in the system, and that decreases the amount of buoyancy that you have to make dots. Okay. So there's an experiment I want to do with this data. I'm going to do 2 things. I'm going to look at the separation of these termination events in time, because that gives me a measure of the overlap in the 2 cycles. Okay. And I'm going to compare it to 2 different things. I'm going to compare it to the sunspot cycle strength in between those 2 terminators, which really makes no sense, but I'm going to do it anyway. And then I'm going to look at the upcoming cycle. Okay, so what does the separation of these 2 tell me about what's going to happen in 2013? Because remember, like I said, the amount of overlap in the system dictates the strength of what you're going to see. Okay, so I'm going to do 2 experiments. The first one, the terminator in between has 0 predictive power. Not shocking. So when I plot all the sunspot maxima from that 270 years of data, all 24 of them, there's no trend. You might as well just plot an average. Okay. Now, and some of you may have actually seen this paper, when I plot them versus the upcoming field strength, you get this beautiful relationship. So when the terminators are separated by only a handful of years, you get very high spot amplitudes. That means that the overlap time between the 2 Hale cycles is small. However, like cycle 24, when the overlap is large, this quenches the amplitude of the upcoming cycle. Okay. Now you will notice that this technique, this correlation, predicted cycle 24's amplitude identically, which is a fluke. But let me tell you that no one in my community predicted cycle 24 strength accurately at all. And in fact, some of you who have been paying attention may have watched the various press releases in the last 1.5 years around the NOAA, NASA consensus sunspot cycle 25 prediction. Just for reference, it's this magenta dot. So what you basically see is if we can predict when the next termination event is going to happen, then we can figure out what the separation of the terminator strengths, the separation of the terminators are. And that gives us a remarkably good data-driven prediction of what cycle 25 will look like. Okay. And so based on analysis that we've done, I guess I'm not showing unless it's on one of the next slides, is that we've timed, we anticipate that the terminator for cycle 24 is actually probably going on right now. The last one happened in February 2011, which means that the cycle strength, the cycle separation is only somewhere between 9 and 10 years. So even if it goes out to February 2021, that puts the sunspot amplitude somewhere around 225. And that actually means that sunspot cycle 25 could be in the top 6 or 7 of all time. Okay. Now, if you believe the data, I'm a strong believer of data. You know, of course, we're interpreting some of this, and the error bars are not totally huge, but you know, 68% confidence, we can say it's going to be around 233 spots, which is double the value predicted by the various numerical models and techniques that were presented to the NOAA and NASA panel last year. Actually, it was a bit longer ago. So just to put that in some reference for you, here is the NOAA NASA projection in orange. It's pretty weeny, looks a lot like cycle 24. Not great for you guys. Probably very good for space infrastructure though. And here's our prediction, which said only really cycle 19 is higher. And I'm going to show you something pretty cool in the next slide. So, and you also get to appreciate a little bit more. Now I've added algorithmically all these other terminator points. So now you get a better feel for when you're in the Dalton minimum, look at the separation between these terminators. It's huge. The amplitude gets quenched. Okay. So it's all about how these Hale cycles interact, overlap, and interfere with one another that creates the sunspot cycle. Okay. Those Hale cycles end, and the terminator events are like a trigger. The death of one cycle gives rise to the very rapid growth of activity on the upcoming cycle. The sun's corona, as measured through F10.7 and a host of other things, responds almost immediately. Ridiculous timescale. You can give me a beer too, it'd be good. Hilbert transforms verify the observational analysis from 1860. You know, our early projection on the Hale cycle was May, plus or minus 4 months. We were right at the very end of that bubble. And I'll show you some data at the end that I was, apologies that we had a false start on this presentation, but I ended up getting sick with pink eye and an infection in my jaw at the same time. But it's actually quite good because it looks like the terminator is happening right now, or if it's not, it will be on the next rotation or there shortly thereafter. So our original projection wasn't too bad, given that nobody's ever done this before. So if I show you the next slide. So I can take the information from my correlation and feed it back in and do a hindcast and basically hindcast what the maximum values were if I just have the terminator separations and my relationship, okay? So these red dots signify what I would have, if I had just the terminators, this is what I would recover, okay? And one of the interesting things here is that it actually, the method under predicts. It gets the low ones very well, and the mid-range ones because there's statistically more of them. But the larger amplitude cycles, it under predicts. And so we're wondering if our error bar is off on the low side, that it may well be that if this does happen, our projection for 25 may actually be low, which would be fascinating. So again, looking at something around 230 spots, maybe a slightly less, could be larger. I would argue that those of us that try to protect critical infrastructure, not really ready for a large sunspot cycle. Funding in my field has decayed over the last 30 years, much the same as solar activity has, because nothing is getting fried in space. Interestingly enough, we have the Parker Solar Probe that you may have heard about or seen, that's flying around the solar system right now, and it'll be a beautiful sensor for that tsunami as it waves itself out through interplanetary space, because this termination event actually does have like a wake that propagates through interplanetary space. So we'll be able to measure that with Parker Probe. Will be pretty awesome. Again, as the Terminator happens, sun's going to go bonkers. One of the things that's a side project that we've been doing is understanding how the Earth's atmosphere responds to those, and it's very interesting for those of you that follow me on Twitter and especially Twitter. You'll know that we actually forecast the growing La Nina state in the Pacific 3 years ago, because the large El Nino oscillations seem to coincide with these Terminator events within 3 or 4 months. So, which is bizarre, but true. Other indicators that we may be right. Sunspot cycle 25 has started showing emergence at very high latitudes. And those of you that are scholars of solar physics or even solar stamp collecting, the higher latitude the early spots occur means that it's going to be a big cycle. Okay, so the tea leaves are also pointing big cycle. Are we there yet? Okay, so I'm trying to look at this myself. I'm going to go back to this plot of F10.7. Okay, and I'm looking for this step function. And what we've basically identified is that when the sun's monthly average F10.7 crosses through 90 SFU, you're basically there, right? So it goes through this step and it never doesn't come back for a long time. And so just last week, F10.7 crossed through 90 SFU. Okay, it's been trying for the last few rotations, and it's it's teetering around 90 right now. But the fact that it's hanging in there, and we actually have a lot of longitudinal structure on the sun. The stuff that I mentioned earlier about Rossby waves and the Gulf Stream and the jet stream is all relevant to this conversation. Okay, so what happens is that these longitudinal, the bands on which the sunspots form actually develop longitudinal waves. And what we're basically seeing here is the start up of those longitudinal wave modes. So I'm watching this like a hawk. This last data point was at 0 UT today. So there's another sunspot group that's about to come across the limb of the sun that will make it bump up again. Now the question is, does it stay or does it recede? If it stays, we are watching like a hawk to see what happens at the sun's equator. If the equator dies, then we're in Terminator, and we will have a very good prediction of what cycle 25 is going to look like. But just for shits and giggles, I'm going to talk about Charles Tree. Okay, just the last few slides and we can get questions. So you remember this plot from earlier. So these are the filaments, sunspots, butterfly pattern. I'm going to show you how powerful these Hale cycles are in terms of understanding the climatology of the sun. Now, Tree is famous for one statistical sleight of hand. Does any of you know what it is? It's called superposed epoch analysis. And this is basically how you determine it and how you look at the average weather on a given day at a given location. And you basically use the fact that the Earth's period is basically a year, and then you stack all your data up on a year timescale. You look at the statistical averages. That was Tree that developed that technique because he was looking for periodicities in sunspot cycles. He never found them because it's far too variable. And the other problem that we have with the sunspot cycle is, remember how I said it varies from 8 years length to 14 years length? People have tried for the best part of 100 years to associate geomagnetic activity to the sunspot cycle. The problem is that the sunspot cycle, if you listen to what I've been saying, the sunspot cycle is not the fundamental mode of the star. The Hale cycle is the fundamental mode, and the sunspot cycle is derived from it. So when you start to look at the Hale cycle, you should start to see patterns emerge, right? So if I can tell you when a Hale cycle starts and ends, then I should be able to turn this, what looks like random junk, into a coherent signal, okay? So I'm going to use the last 24 years of data. And if I can get my little zoom thing to appear over here, sorry, I made all disappear, sorry. This is one set of observations. So this is of the sun's corona, and it's 24 years of data. And I'm going to slice this based on the termination point. So you see, this is the most, this is the early data. So it's the blue, it's the red chunk. And then there's the blue chunk. So I'm taking the Terminator plus or minus 11 years. And then I'm taking the green chunk, so here to here, and then the orange chunk. So this is the most current data, okay? And the sharp-eyed, those of you, will notice that the pattern appears to recur. The set of images on the right-hand side is from the sun's interior. So this is pathways that the magnetic field takes as it moves through the sun. And I do the same thing. So the sun's magnetic field on the inside is replicating itself on the outside of the star. That's no big shakes. But let me show you what happens to that pattern. Again, using Tree's technique. So if I start to roll an analysis window through the time series, and then I build a statistical average, you'll notice that there's a basic unit. Okay, that's only 24 years of data, however. Now, if I apply that same analysis trick to a record that I have of the sun's 5303 green line, so this is actually emission from iron 16 or 15 times ionized iron, so it's about 2.5 million degrees, you see the same thing. So I step through one window at a time, and I stack them all up, and I show you what the mean looks like. So if I can pause this, boom, that's the mean variation of that time series, right? It's beautiful. So basically, using these Hale cycles, I can decompose this nasty mess into something that makes sense. If I look at 140 years of my prominences, now this is a little bit more ratty, but you'll see that it does the same thing. Here's the coup de grace, the random sunspot butterfly pattern. Isn't so random when you know when it starts and ends. So again, if I take my analysis window through, butterfly, 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 one at a time, plus or minus 11 years around the termination point, I get to a beautiful pattern where all of those butterfly plots basically align on top of one another. Okay, so what this basically telling you is that the Hale cycle is underlying all of this stuff. And just compare, sorry, this is flying through. but I'm going to step through this one at a time. So here's all these different diagnostics, okay? There's my butterfly diagram. Whoa, sorry. Lost control. Okay, here's my butterfly diagram. There's my schematic. There's sunspot butterfly. There's prominences. There's the coronal emission. There's my contemporary data. There's the model, okay? So basically, when I go back here, show you the sunspots are truly only a portion of the whole. Now, my colleagues that are working on this problem only work from the sunspot record. They do not work from the rest of it, the other 10 years of overlapping stuff. So you can possibly imagine why this is a challenge. So anyway, to conclude, the 22-year Hale cycle is recurrent and robust. The bands of the Hale cycle have a definitive end that we've called the Terminator. The Terminator triggers growth of emergence of magnetism at about 30 degrees and about 55 degrees. We can get into why 55 degrees in a little bit, but it's pretty cool. Terminator sees a massive jump in solar proxies, like F10.7. Our 24 hypothesis is the bands of the Hale cycle contrive to modulate. It's an interference pattern, and that interference pattern basically sets the sunspot pattern that you get, okay? Terminator separation is one measure of the interplay between the bands. Long terminator separation yields small amplitude cycles, and conversely, short separations give rise to big cycles. If the terminator happens soon, it means that sunspot cycle 25 could be huge. The relationship underestimates big cycles, so it could be actually bigger than huge. I don't know what that is. Gargantuan, massive, I don't know. Pick a better superlative. The terminators, the ends, the Hale cycle termination points provide a very good, robust clock to understand solar activity. And this is the crux of, from a solar physicist standpoint, is demonstrating that the sunspot cycle, what everyone has assumed to be fundamental mode of the star, is a byproduct of the 22-year Hale cycle beneath it. Okay, that's something very important to take home. The Terminator itself seems to be, if it's not going on right now, it's very, very close. But I would argue, as I said earlier, we are really not ready for a massive sunspot cycle. As someone that deals with this stuff, or have done at the kind of government level, nobody's prepared. They all think that the sun's in a steady decline. And I don't believe that's what the data is telling us. But anyway, with that, I will open up to questions that you may have. And I thank you for your patience. And I know I've taken a long time.
That's pretty fascinating. The Hale cycle is the key.
The Hale cycle is the key.
Yeah, and the shortness, I could see the shortness between the two terminators, and it looks like it's really close, closer than I've seen other years. So just like before the 1950s.
Right, it's getting very close. I mean, this is 9 years.
Scott?
Yes.
Scott, do you have